So this is my code for a one-dimensional random walk in which these steps are to the left and right or forwards and backwards by a unit, single unit of one step. So for the code, in this first cell here, I'm importing numpy and I'm importing matplotlib. I want some random numbers, so I need numpy. I want to make some plots, so I need the matplotlib. In the second cell, I'm just defining a few things, a few quantities, a few variables that'll be useful to me. Actually, the first thing I'm doing, I've mentioned this in class, is that random number generators need a seed, a starting number, and you can set the seed or the starting number for your random number generator. And that's a useful thing to do. If you set the same seed, you'll get the same sequence of random numbers. And if you set a different seed, you'll get a different sequence of random numbers. And sometimes it's helpful to be able to set the same seed when you're developing the code and get the same set of random numbers. Other times it's useful to set different seeds, so you get different sets of random numbers and different statistical distributions. So that's the call to this seed function in the numpy random number package. I also define a list and an array, a list called moves and an array called colors. This is just handy things for me. So as I mentioned, in this random walk, we're going to step left or right, forward, backward, positive, negative, by 1 unit, randomly. And I've made a list that contains the possible steps, 1 unit forwards, 1 unit back. That's what the list moves is. And I'm going to use that when I generate the random steps. So it's just a handy thing for me. When I'm plotting the path, the random walk, I'm actually going to overlay many random walks. And one thing that's handy in just visualizing the random walks is to color different random walks with different colors. And so I'm just defining this array of strings, which will be used to define different colors when I do the plotting. So red, blue, green, magenta, cyan, yellow. So those are just useful things for me. In the next cell, I'm going to define some of the parameters of the problem, and I'm going to initialize, I'm going to declare some useful arrays for the calculation and for the plotting. So firstly, 2 numbers that I'm defining, 2 variables that I'm introducing here are the number of particles in my calculation and the number of steps in the random walk. So right now I've set the number of particles to be 1. I'm just going to follow 1 particles random walk, and I'm going to follow that random walk for 100 steps, just 100 steps. And later on, when we make plots, I'll change the number of particles, for example, so that we can look at a statistical distribution of walks rather than an individual walk. These 4 arrays here, these 4 arrays have dimensions of the number of steps. So they would, if I run the code like it is right now, they'll have a dimension of 100. So the first array that I call step is simply an array of the index of each set. So I've got steps, 1, 2, 3, 4, 5, and so on. And I'm just making an array called step that carries that label, that carries that index. So that's just going to be handy for the plotting. The second array, the one I've called path. So this array is actually going to contain the path, meaning the location of the particle after every step for the last particle that I've generated the random walk for. So it's just the full path, the complete path through our one-dimensional space of the last particle that I've generated the random walk for. There's two more arrays that are kind of tools in making a calculation of two quantities. One is the mean range of the particle, the mean displacement of a particle if you carry out many random walks. And the other one is the root mean square range of a particle if you carry out many walks. Now, we talked about these. The mean, if we generate steps forwards and backwards in an unbiased way, the mean should be zero. The mean displacement will be zero. We'll have as many particles walking left as right. The root mean square, which means I square the displacement of the particle and then average that and take the square root to get the root mean square, that will be non-zero. And we talked about that. We said that the mean square is actually equal to the number of steps. The root mean square will be equal to the square root of the number of steps. So these two arrays are just tools for me to be able to calculate that mean displacement and that root mean square displacement. They're tools because I want to average many tracks. And these are the arrays that I'm going to do that averaging with. These are the arrays that I'm going to do that summing that I need for the averaging. Finally, there are two more arrays downstairs here. These two arrays are not of dimension the number of steps. They're the dimension of the number of particles. The first array just contains the label for the particle. It's particle 1, 2, 3, 4, or the index of the particle, saying it's particle 1, 2, 3, 4. And the second array is going to contain the final range of the particle, the final displacement of the particle. And so those are two other arrays that I used in this computation, in this simulation. This next cell is where I carry out the random walks. In this cell, I've got control statements, for loops, actually nested for loops, to carry out the random walks of the particles that I'm simulating. So the first loop upstairs here, this is a loop over the number of particles. Now, right now, I've set the number of particles to be 1. So this will just be for that first particle, that particle number 1. But if I'm simulating many particles, then we'll go around this loop many times. And inside that first loop, I just assign the initial position, the initial location, I've called it the variable x, to be the origin for the particle. So the particle is going to start walking away, randomly walking away from the origin. The for loop inside the particle loop is the for loop over the number of steps. It's this guy here. So this is where I start walking the particle or the particles away from the origin. And this is a for loop over the number of steps that I'm going to take. So in my case, I'm going to loop around this for loop 100 times because I defined the variable representing the number of steps to be 100. The first thing I do in this line here is call a function in the numpy library in the random package. It's this function choice. This function choice takes an argument that is a list, and it will randomly pick one item from that list. Uniformly, randomly pick one item from that list. Now, my list, I called it moves, was just a forward or a backward step. a step of +1 or -1. And so it's just going to randomly pick a forward or a backward step, a step of +1 or -1, and it's going to move the particle by that amount. Look, here it's changing the position of the particle by that amount. After taking that step in the random walk, and when I go through the loop, it will take all the steps in the random walk. After taking each step, I record the location of the particle in the array path. So that's so that I can plot the random walks of different particles. And then I also increment these two other arrays, the mean array and the root mean square array, that are going to allow me to calculate the mean displacement of the particle after a certain number of steps, the root mean square displacement of the particle after a certain number of steps. After completing the loop for a given particle, after carrying out all the steps in the random walk for a given particle, I plot the path of the particle versus the step. So if you look at this call to this plot function, I'm passing two arrays, the step array, which is just the label of the steps, and the path array, which records the positions of the particle on each step. And so this will just plot the trajectory. At the bottom of this cell, I kind of complete the calculation of the mean displacement of n particles, however many particles I've generated, and the root mean square displacement of the n particles that I've generated, so that I can look at those quantities too, those mean displacements, statistically mean displacements, and the statistical root mean square displacement. Let's run this cell. And when I run this cell, here you see the path of an individual particle. So it first heads negative. Oh, sorry. It first heads positive in the positive direction. It then starts heading back towards the origin. And then over here, it's actually gone in the negative direction. And so we're seeing this random walk. If I was to make the number of particles 6, then I would see the 6 random walks that I can actually color with these 6 different colors. So let's just try 6 random walks. And here we see those trajectories. So we're seeing each particle randomly walk, and their paths are different. And we can see that quite clearly. And we see how as they walk away from the origin, right, they're spreading out as they walk away, as they randomly walk away. They're kind of diffusing outwards. Now, you notice in principle, a particle could get in 100 steps, it could get 100 steps in the forward direction, 100 steps in the backward direction. That's extremely unlikely, though. You'd have to throw 100 heads in a row. You'd have to throw 100 tails in a sequence to get those extreme random walks. And we don't see that here. With 6 random walks, it's highly improbable to see that. If I was to take 100 particles and see their random walks, overlay their random walks, I get this plot here where you kind of see the overall average of what's happening. You see this swarm, this kind of shower of particles walking away from the origin with some mean displacement. You can picture this on this plot. The mean displacement looks like it's around 0. I mean, there's as many going up as there is going down on the plot. There's as many going forwards as backwards. But you see that the root mean square displacement, if I'm squaring the displacements, then both those squares are positive. The root mean square displacements, that's going to be non-zero. And it's sort of the scale of 10. And 10 is the scale that you would expect, because we said the root mean square displacement is the square root of the number of steps. So at least qualitatively, this bears out that statistical argument. I'll make a couple more plots down here. So in this cell, I'm plotting those two other quantities that I calculated, the statistical quantities that I calculated. It was the mean displacement for however many particles I generate, so 100 here, and it's the root mean square displacement for however many particles I generate here, again, 100. So on this plot that I created in this cell, horizontally, I got the number of steps. Vertically, I've got either the mean displacement for the 100 particles or the root mean square displacement for the 100 particles. The mean is in green. The root mean square displacement, RMS, is in magenta. And you see clearly on these plots the statistical nature of the random walk. So we said that we expect the mean displacement to be 0 if we generate many particles. 0 within the statistics of however many particles we generated. Here we generated 100. And that's what you see in this green line, essentially. This green line is centered around 0, and it's saying on average, this is many particles going forwards and backwards. The mean displacement is 0, statistically 0. However, the root mean square displacement, which is this line here, the magenta line here, we said that's not statistically 0. The particles will diffuse away from the origin where they started. And the rate at which they diffuse away from the origin is that the root mean square displacement is equal to the square root of the number of steps. And so you see at 100 steps, if we pick that, the square root of that is 10. And we have a root mean square displacement that is 10. If we were to pick, say, 25 steps, the square root of 25 steps is 5. And you see here that the root mean square displacement is 5. And so both these curves bear out a statistical understanding of the random walks. There was one final quantity that I calculated. I calculated the range of each particle for its 100 steps. And this plot is the distribution of those ranges. So at 0 here, this central bin this is the number of particles that remained around the origin. Over here on the far right, and over here on the far left, plus 25, minus 25. This is kind of the extreme range of the particles, the number that got to about 25 or got to about minus 25. So here you see the distribution of ranges of the particles in the random walks for 100 different random walks, for 100 different particles. Anyway, this code is an example of random walk in one dimension. It's a simple random walk in one dimension where the steps are the same size. There are always steps of plus or minus 1. So it's, in that sense, the simplest random walk. But it's a template for how you would calculate more sophisticated, more complicated random walk. So if you were walking in 2 or 3 dimensions, you'd have additional steps, components of steps in those extra dimensions. If your step sizes were different, you would have a core to create a call to a random function that would create different step sizes. If you could take steps in different orientations rather than just forwards or backwards or up and down, you would have another call, a call to a random function to randomize the direction in which you step. So it is a template. It is the basis for much more complicated random walks in more dimensions with more variables. And it is a template for understanding Brownian motion.